let's write the complete electron configuration for these three group 1 elements: lithium, sodium, and potassium. Notice here that I've underlined the valence electron in each of these cases, and as all group 1 elements do, these three have a single valence electron. Now, you should have learned in your studies of atomic structure that this coefficient out front, this 2 here, or this 1 here, represents the energy level that the electrons are in. So lithium has 2 energy levels of electrons. There's the first one, there's the second one. Sodium has a first energy level, and then a second energy level, and out here a third energy level. So I'm going to represent sodium with 3 rings around it. Potassium has 4 energy levels. So I've showed the nucleus here. That's the little dot in the center. And then 1, 2, 3, 4 rings. And this brings us to the idea that in any group, the element below has 1 more occupied energy level than does the element above. There's a new layer of electrons every time you go down one element in any group or any family, which tells us that atoms are a lot like ogres. They have layers. Or atoms are a lot like onions. They have layers of electrons. This brings us to the idea of atomic radius, which is simply the size of a neutral atom. And of course, the size of an atom depends mostly on where the electrons are, how big the electron cloud is, because the nucleus takes up a very tiny fraction of the total volume of an atom. As we go down a group, the atomic radius increases. You can see that in the upper right corner. As we go down a group, the atomic radius increases. And this is because we add a new energy level of electrons every time. So, as we go down a group, the atoms get larger because we're adding new layers of electrons with every transition. Now, what about if we go from left to right across a period? Well, in that case, the atomic radius gets smaller, which at first might not seem to make sense because the masses of atoms certainly increase as you go from left to right. The number of protons increases by 1 every time. So let's try to get our heads around this by discussing columbic attraction, which is a very scary sounding term for something that's very simple. And that is that columbic attraction is simply the attractive force between positives and negatives. Opposites attract. Columbic attraction depends on the amount of charge that we have and how far apart those charges are. The more charge we have, the stronger the columbic attraction. The farther apart charges are, the weaker that interaction. If you've ever played with magnets, you'll understand this. Magnets can be strong or weak. The stronger 2 magnets are, the stronger they're going to interact with each other. The further apart those magnets are, the weaker their interaction. It's the same idea with columbic attraction. So here's my very bad analogy to help you try to understand what's going on here. So we have 2 carts. They're connected by a spring in the middle, and what I'm going to do is I'm going to put a positive charge in one cart and a negative charge in the other. Well, the positive and the negative are going to attract each other. So won't the cart system crimp together a little bit In other words, it'll be a little bit smaller than it was when it started. If I put a second positive somehow and a second negative charge, won't the cart system crimp together even more closely? Because now, instead of having a single positive charge and a single negative charge, we have two positives and two negatives. So here's the point. This cart here has less mass because it only has one positive and one negative, but it has a larger radius. The cart on the bottom has more mass because there are two positive charges and two negatives instead of one each. But even though it's more massive, it's smaller. This is what happens with elements when we're going from left to right across a period. The mass increases, but in general, the size of the atom decreases. So, going from left to right across a period, atomic radius decreases because there's more coulombic attraction with no new energy levels of electrons. I should add that. Therefore, there's more pull, a tighter pull, a greater pull, and therefore the radius is smaller. So, periodicity trend number 3 goes like this. Atomic radius increases going down and to the left. And here we have the S and P blocks. I've taken out the D block just so you can see the pattern. But just in glancing at that, you can see that, yes, in general, as we go down any group, atoms get larger. And we know that that's because we are adding a new layer of electrons every time we go down one element in a group. Furthermore, as we go to as we start on the left side of a period and move to the right, you can see that in general the atoms get smaller. They get more massive. In other words, they have more mass. They're heavier, but they take up less space. Now, there are some exceptions. We're not interested in the exceptions, but we're just learning the overall pattern. You can see that here, aluminum's atomic radius is actually a bit larger than gallium's. Now, if I were to ask you, who has the larger radius? Who would you predict has the larger radius, aluminum or gallium? You should say gallium, because it's the pattern that we want you to know. And there are a few other exceptions as well. But in general, as we go down a group, atoms get larger. As we go from left to right across a period, atoms get smaller.